Okay, so as an organizer, I invited myself to speak, but my goal would be very modest. I would provide some of the background and general information that is needed to understand what Draw and other people are talking about, some general information about SCV. I'd also like to look at some examples and start at the other end. So instead of looking at general complex manifolds, I would like to start from very simple domains in the plane and stuff like that, so that at some point what I'm talking about and what Rod is talking about will come together. Also, there is a practical announcement that Divya asked me to make. So those people who are traveling from IISc, please take the 8:40 shuttle, because the 8 o'clock shuttle is a smaller vehicle which doesn't have enough space. So you are all requested to ride the 8:40 shuttle. Okay. So let us get started. So we'll start from the very beginning, which is to say we'll recall the most important case of several complex variables, which is one complex variable. So I looked up the dictionary the other day. It says several means many and a small number but not one. But for our purposes, several also does include one. So let us begin with our heroes, the holomorphic functions. So as you know, they can be defined in many, many different ways. Let us recall a few of them. So we have a function f. This omega is an open subset in the complex plane. So what do we mean by saying f is holomorphic? So there are various popular definitions. One of them is that the limit as h goes to 0 of f of z plus h minus f of z divided by h exists for every point z in this open set. Another equally popular definition is that f satisfies, so f is C1, let us say, and f satisfies the topic of this workshop, the Cauchy-Riemann equations. And I'm sure everybody knows what they are. One way of writing them is, if you write in terms of real and imaginary parts, it says that du over dx is dv over dy, and dv over dx u over a system of linear partial differential equations. Another equally popular definition, no, but I shouldn't say equally popular, another definition, probably not so popular, f is continuous on omega, and for each triangle, by triangle I mean solid triangle, let's call it a triangle contained in omega, if I integrate f of z dz along the boundary, I get 0. Right? So depending on your point of view, this is either a theorem or a definition, but this also defines exactly the same class of functions. And finally, f is complex analytic, which is to say, for every point A in this domain omega, I can write f of z is sum of some number Cn, z minus a to the power n, n goes from 0 to infinity for z near a. So there's a power series expansion in the neighborhood of each point. So depending on your taste, you can take any one of them as definition, but for our point of view, this is the natural definition. And we prefer to write this using the Wettinger derivatives. Let us quickly recall what they are. So the d over dz operator is 1/2 d over dx minus I times d over dy, where I is the square root of -1, and we also have the z bar derivative, which is just its complex conjugate. And once you have introduced these, the Cauchy-Riemann equations they take the compact form df over dz bar equal to 0. So a holomorphic function is one which satisfies this equation, this one equation with constant coefficients. So one thing that I need to point out here is that I said that f was C1 in this definition. This is not really necessary. So what an important fact, f does not have to be C1, but then one asks how one takes the derivative. So if f is a distribution, or even a more singular object like a hyperfunction or something, such that df over dz bar is 0, then f is a holomorphic function in the usual sense. So this definition already incorporates this refinement. Okay? All right, so having recalled that, let us introduce the inhomogeneous, so our hero, or the simplest avatar of our hero, the inhomogeneous Cauchy-Riemann equation. So here we have a function which is killed by the d over dz bar operator. So the equation we want to study is du over dz bar equal to g, where as usual g stands for given and u stands for unknown. And this is the d bar equation in one variable. So the whole idea of all we are doing here is to solve higher dimensional analogues of this equation. But today we are going to restrict ourselves to just one dimension and see how to solve this, at least one way of solving this, and look at some properties of this equation. So the first question one should always ask in anything is why? Why do I want to solve this equation? And the answer is very simple. This is to construct analytic objects. So analytic objects, roughly speaking, are things which are locally described by holomorphic functions. Okay? So including holomorphic functions themselves, meromorphic functions, and so on. Okay? So let us look at an example. Let us look at a classical example of the application of the Debraj problem to solve, to construct some kind of analytic object. So let us recall what I will call the Mittag-Leffler problem. So it's a theorem, but right now, since I don't know it is a theorem, or at least I'm pretending I don't know it's a theorem. So please forgive me if the spelling is wrong. So basically we are in the following situation. So omega is a domain, which means an open and connected subset. And we are given a subset A in omega. So this A is a countable set. So J goes from 1 to infinity. Countable. A has no limit point in omega. So therefore, if you look at the points of A, of course, if omega is, for example, bounded, it will have accumulation points in C, but they are all on the boundary of the domain omega. Yes. Oh, no, it's not a conclusion, okay. So it's a property of A, okay, such that A has no this. Yeah. Okay. And suppose for each such point A, so for all these aj's, for all j, I am given a function fj, which is, this O stands for holomorphic. Okay? Because in, I think, what I heard was that in French they say holomorph, but a Frenchman corrected me. It is from the Italian, where they say holomorfico and write with an O. So O stands for holomorphic. So O. Okay, okay, so it comes from Kronecker. There's no reason behind it. Yeah, okay, okay. So O. Okay, so O. So this is a holomorphic function in a punctured neighborhood of the point aj. So by B star of A epsilon, I mean the set of points in the complex plane such that 0 is less than mod of z minus A is less than epsilon. Okay, so therefore, if I'm allowed to draw a picture, so this here is omega. A is some point which is thinly distributed but accumulates on the boundary, and for each of these points I have this small neighborhood in which I am given a holomorphic function which may have a singularity at the point aj. Okay? So these are the principal parts, and then the goal find a function holomorphic on omega minus A such that near each aj, f is of the form fj plus h, where h is holomorphic at aj. Okay. So for example, what's a good example? So let's look at one of the classical functions. So let's look at the function, for example, cotangent of pi z. Okay? So, which is cosine pi z divided by sine pi z. So that from this I see that this has poles at each point of z. Right? You plug in any integer, this vanishes and something goes wrong. So what we are asking here is sort of a reverse question. I'm given the poles and I'm given the behavior of the function near each pole. Can I reconstruct it? And as you know, this can be done, but we are going to do it in a slightly different way, and which will show the importance of the, I think I should reinstate this f here. So find f such that I'll say that f minus fj extends holomorphically to the point aj. So now I have the following. Suppose omega has the following property. So if I take a function g, which is smooth in the interior of omega, there exists a function u, also smooth in the interior of omega, such that this u is a solution of the inhomogeneous Cauchy-Riemann equation with g the right side. Suppose I can solve every such equation. Then the Mittag-Leffler problem has a solution on omega. I think I should be more precise here. Every Mittag-Leffler problem has a solution. And that is easy to see. And that leads us to how one uses the Debraj problem to construct this object. So step one. So choose a cutoff chi j, which is C infinity with compact support in C, such that chi j is identically 1 near aj and identically 0 outside the ball centered at aj and radius epsilon j. So these choices depend on the particular data. Okay. So what I did here was that at each of these points, I chose a cutoff which lives near this point. Okay. And now let us look at the function. The function, I need a name for it, let's call it f tilde, which is equal to chi j times fj on the punctured neighborhood aj epsilon j and 0 elsewhere. So this is sort of like a Jugaad's solution of the problem. So what have we done here? We have basically taken the data, which is a function with a singularity at aj, cut it off and put them all together. This is of course not holomorphic, and all we can say about it now is that it is C infinity on omega minus this set A. Okay, and now we are going to change this f tilde so that it is a solution. So let us look at the function g, which is given as d bar f tilde on omega minus a and 0 on each point of a. Let us see what we can say about this function. So my picture is somewhere there, so I will draw a second picture here. So this here is my aj. This is the neighborhood of size epsilon j. So what can I say about d bar f tilde near the point aj? So what can I say about this f tilde near aj? It is equal to fj, which is holomorphic. So therefore, what can I say about this d bar of f tilde near the point, near each point aj? It is, and therefore what can I say about this function? This function therefore belongs to C infinity of omega, because I just extended what was 0 by 0. Is that clear? So now, by hypothesis, there exists a solution, smooth solution of du dz bar equal to g. And now let us look at f. Now I have to see, no, my notation is here, which is f tilde minus u. Let's look at this function. Okay? So where is this function defined? This is certainly, I already know that this function is C infinity on omega minus a, because each of these functions is. And what is d bar of f? I should not be using this. I'll go back to my old notation. This is what I mean by d bar. Okay. What is df over dz bar? That is df tilde over dz bar minus du over dz bar, but this guy is g, which is therefore equal to 0. And near each aj, f is f tilde minus u, but f tilde is fj near each aj, as we saw there. And what do I know about u near aj? Near each aj, g is equal to 0. U is holomorphic near each aj. Since gj is 0 near each aj, in a neighborhood of each aj. Okay? So, and we are done. Yeah, the U is holomorphic, including at the point AJ. Yes. F tilde is already a solution. Yes. Yes. So this guy U is holomorphic near and at each AJ. Yeah. Thank you. Is that clear? So this is the sort of model of the use of the D-bar problem to construct holomorphic objects. All the other applications basically follow this same idea. So you want to solve a problem, construct some analytic object, you sort of fudge it up, you solve it in the C infinity category, which is what we did when we constructed this guy F tilde. And then we solved a D-bar problem to correct this solution so that we got the solution that we wanted. So I have therefore probably impressed upon you the importance of solving this problem. Okay, so now we come to a very, very important result, or I should say very simple special case of a very important result, which tells us one way of solving the D-bar problem. So this is I should say one version of Hormander's theorem in one variable. Again, one should note here that this is one of the rare cases where a result was first proved in several variables and then the one variable case was extracted. So let us go right ahead and state this result, and then we'll spend the rest of the day today and probably some part tomorrow in trying to prove it. Okay, what is this Hormander's theorem, which we want to study? So now again, we have omega, which is a domain in C. Phi is a real valued C2 function. And we have to make a very important assumption about phi. We'll assume that the Laplacian of phi, by which I don't mean what Laplace meant, by which I mean almost what Laplace meant, except it differs by a factor of 4. Okay? This quantity is greater than or equal to C, which is itself greater than 0. So the Laplacian is strictly positive and bounded below. So this, we would say, strictly subharmonic, or even better, uniformly strictly subharmonic function. Okay, and now I am given a function g from omega to c. I'm writing measurable, but soon I will forget writing that because, non-measurable functions are not much fun. But what this measurable function does is that if I square its absolute value and integrate it against e to the power minus phi over omega, this is finite. Okay? So it is in L2, in a weighted L2 space. Okay? All right? And then I will remove this. This name is of absolutely no consequence. I think I have all the hypotheses. And the conclusion, there exists a function u from omega to c such that, first of all, let me say the more important thing first. Du over dz bar is equal to g, and we have an L2 estimate on this one. So the mod of u square e to the power minus phi dv is less than or equal to 1 over c Is clear? So several things need to be pointed out here. What does this mean? This u is an L2 function. How will we differentiate it? So if you want to be really precise, this equation holds in the sense of distributions. And the other thing I want to point out is the very close relation between the Laplace operator and the d over d z bar operator. Okay? So this has many important consequences, and we'll look at a few of them later. Okay? So this is the theorem that we want to prove. Okay. So let's see how one does that. So first, we will need a tool which, following draw, I will call the function analysis lemma. So what is this function analysis lemma? So let me state it first, and then I will explain the various terms that occur in it. So H1 and H2 are Hilbert spaces. And T from H1 to H2 is a closed, densely defined linear operator. And I will define what these terms mean in a few minutes. And let alpha be an element of H2 and C be greater than 0 such that, so now I have to be careful and look at where the C actually occurs. Such that for all beta in the domain of the adjoint of T, we have the following inequality, that the norm of T star B is bounded below by 1 over C times the absolute value of beta alpha for all, I have already quantified beta. Is the statement clear? I have not defined a few things. I have not said what is the adjoint and what the domain means. It's some subspace. So the norm of T star B is bounded below by this quantity. And then with this hypothesis, I have the following conclusion. There exists a U which is in the domain of T such that Tu is alpha, and we have some idea about the size of U. The size of U is less than or equal to C. Okay? So those of you who have seen things like Lax-Milgram lemma or other existence results starting from inequalities will find this very similar. So what this is doing is it is taking an estimate, an inequality, and with that we are able to solve an equation. So it's a very powerful thing. Okay, so let us see what the various terms mean. So suppose now T is an operator. So these dots mean that T is defined on a subspace, on a linear subspace of H1, and this linear subspace, so this linear subspace is called the domain of the operator T, and this domain T is dense in H1. So that is what it means to be densely defined. Since our T is ultimately going to be some kind of differentiation, we can't allow it to be defined everywhere, but it is densely defined. Okay, that's what it means. Okay. Yeah? The different Hilbert spaces. Okay, let us, since all our applications will be separable, therefore let it be separable. Yeah. I don't think I'm using it anywhere, but yeah, there's no harm in making that assumption. So, we have perhaps a separable Hilbert space, and we have something, a linear operator, which is defined only on a dense subspace. I'll just give an example in a few minutes, okay? And it is mapping into some H2. And then what does closed mean? This means you look at the graph of T. Graph of T, this is the set of x comma T of x, where x is in domain T, which is a subset of H1 cross H2. So you look at the graph of this operator, which is a subset of H1 cross H2. So to say that T is closed means this graph of T is a closed subset, in fact a closed linear subset, closed subspace therefore, of H1 cross H2, which is itself a Hilbert space in a natural way, right? You take the product of two Hilbert spaces, you get a Hilbert space. There's another way of thinking about this which is kind of valuable, so let me point out that also. So now, another point of view. So let us look at the domain of T, and introduce a norm on domain of T. So suppose for f in domain of T, define the graph norm to be given by the norm of f in H1 squared, which makes sense, f is an element of H1, plus norm of Tf in H2 squared. So with this, so this makes domain of T into an inner product space, an obvious inner product. And I leave it to you to check. So T is closed means that domain of T is a Hilbert space. It's a complete in graph norm. All right. So I have therefore explained. Let us see what I have explained. I have explained closed. I have explained densely. I don't have to explain linear operator. I'm sure everybody knows that. Okay. Next thing I have to explain is what is adjoint and what is its domain. So what I am going to do, I am going to keep these two boards and work around it. Okay. So, morally speaking, an adjoint should be something that satisfies this, and the definition of the adjoint of an unbounded, again this unbounded just means possibly unbounded, possibly not bounded operator, is defined in such a way that this equation holds. So how is this done? So we define first the domain of T star to be, okay, now one has to be careful, all G in H2 such that the map F goes to TFG. So this is a map from H1 to C is a bounded linear functional. So that once you have this definition, you can easily check. Now I have to skip these two boards. I also have to skip this board. I have left with only one. Okay, I'll use that. So if T is closed and densely defined, then number one, domain of T star is a dense linear subspace of H2. And number two, T star, which is a mapping from H2 to H1, is closed. And number three is what we wanted. For every alpha in domain of T and beta in domain of T star, we have what we wanted. T alpha beta is exactly alpha T star beta. So this here is the inner product in H2, and this here is the inner product in H1. Okay? So you get basically what you wanted. So I have now, I think, let's see we have defined everything or not. I think we have. Right? I didn't define T star. Oh, I was hasty. So I have to define T star now. Okay, so I have to come back here. So I will now go from top to bottom and define T star here. So let's analyze what it means. What does this definition mean? Okay. So we have the map from H1, or even better, I should say, domain of T, which is a dense subspace of H1, into C, given by F goes to TFG. So this is bounded by hypothesis. Which means, let us recall, that is, if I look at the absolute value of TFG, this is less than or equal to, so I have used C for various purposes. Let's call this K for a change. K times the length of F in H1. Right? Bounded linear functional. And it is defined on a dense subspace. So therefore, this functional extends, let's call this functional something lambda. So lambda extends by continuity to an element of H1 star, the dual. Right? We have something defined in a dense subspace, it extends. What do we know about the dual of a Hilbert space? Suppose you have a bounded linear functional in a Hilbert space. Yes, please? Yes, and what is that isomorphism? So therefore, there exists some T star G in H1 such that this lambda of F, which is by definition TFG, is the same as F T star G. Is that clear? And therefore, this defines E star. It's exactly the same definition as for bounded linear operators, except that you have to take care of the domain. Okay. All right. So I think I have explained this lemma, right? Okay, what the things mean. Now I will prove it, which is much, much more simple than explaining the meaning of the terms. So proof of the functional analysis lemma. It's more or less obvious. So, okay, consider the map xi from the range of T star to C given by xi of T star beta is the inner product beta comma alpha. So this alpha has been frozen once for all, right? So this alpha is fixed in this theorem. Okay. What can I say about this xi? Huh? Yes, please. Is there such a xi? The first thing is xi well defined? Yes. Xi is well defined. Why? So suppose this inequality. This inequality, yes, of course, yes. Very good. So if, okay, T star beta 1 is the same as T star beta 2, that is T star of beta 1 minus beta 2 is 0, then observe that xi of T star beta 1 minus xi of T star beta 2 is, what is it? It is beta 1 minus beta 2 comma alpha, right? And now if you try to estimate that, that becomes so that has to be 0, right? Because T star beta 1 is equal to T star beta 2, right? All right. The second most important thing is this xi is bounded. That is obvious because of that inequality. So I'll give this inequality a name. Xi is bounded by star. And what happens, so therefore we can extend, we did do exactly what we did a few minutes ago. We can extend xi to an element of, so now where is it defined? Element of the dual of H2 star. Okay. And again by the Rie's representation theorem, so by the Rie's representation theorem, there exists a U such that xi of gamma is the same as H1 star. Let us check that. Yeah, you are absolutely right. It is H1 star. Thank you very much. Yes. So xi gamma is the inner product of gamma with U, right? So by the Rie's representation theorem. And again, I have, yeah. Say that again? Yeah. Yes. Yes. I defined a map xi by this formula. This is the definition of xi. Yeah. Yes. Yeah. 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 Right? Okay, now I have to rush to the other end of the board again. Or maybe what I will, with your permission, I will erase this.
But it has a little bit more argument. Psi can be extended to the whole group.
I think we said that. With the same norm. Yes. Okay. Yes. With the same norm, right. So in the case of Hilbert spaces, this is very easy, right? You just define it to be 0 on the orthogonal complement. Okay. By Riesz representation theorem, there exists U, which is this, and norm of U is actually equal to the norm of xi as a linear function. Okay, and we are almost there. So now you choose gamma to be T star beta, where beta is in domain of T star, and let's see what that gives me. So if I can read it correctly from here, I see that xi of T star beta, which is by definition beta comma alpha, is by what we saw there the same as T star beta comma u, which shows that u is in the domain of T star star. And it is not difficult to show that this guy is basically the same as T, so which means u is in the domain of T, and now I can move T star to the other side, which means beta comma alpha is beta comma Tu for all beta in domain of T star, which gives that Tu is alpha because the domain of T star is dense. Is that clear? So this is the tool that is going to be used in order to prove Hormander's theorem. Okay? So therefore, what we really need in order to prove this result is an inequality. Yes?
T star star equals T, not a general fact. Only true for closed density.
That's correct. T star star is only true for, yeah. In general, it's an extension. It's going to be an extension of T defined on a larger domain, because T star star is always going to be closed, whatever T is. So therefore, so here we need very much the assumption that since T is closed, densely defined. Okay, so we need a certain inequality now, right? An inequality that will lead to this proof. And the rest of today and most of tomorrow will be devoted to the proof of that inequality, which can be used to. So this is the basic estimate of L2 or at least one basic estimate, our basic estimate. Okay? So this is what we will devote ourselves to. So in order to use this, I will need certain closed densely defined operators. So let us define few closed densely defined operators. So to apply the function analysis lemma. So this is one of the very happy situations in which H1 and H2 are basically the same space. When we go to several variables, or even when we do the one variable case in a more invariant way, we'll need to consider different H1 and H2. But right now, I will have only one Hilbert space to consider, which is the space which I will write as L2 omega phi. This consists of f from omega to c, such that the integral mod f square e to the power minus phi dv over omega is less than infinity. So it is a Hilbert space with a weight. So this phi is called a weight, which is just another name for a real valued function. So when I was an undergraduate student, I once asked my linear algebra professor, what is a scalar? This is another name for a number. Then I was kind of very confused, why do you want to call numbers scalar, So, so the story is similar here. The weight is certain positive real valued function which you have fixed on this domain. So this is the only space. So this is my space, which is both H1 and H2. And my only operator, I will denote it like this. So introduce this operator. So this is going to be a densely defined operator, closed densely defined operator, closed densely defined from L2 omega phi to itself. Okay? And let me define this. So as we just learned, in order to define a closed densely defined operator, the first task is to decide on the domain. What is the domain of this operator? So the domain of this operator d bar consists of those functions f in L2 omega phi, such that if you take df over dz bar, that also belongs to L2 omega phi. Of course, this derivative is a distributional derivative. Is that clear? So what are some functions in this domain? I think now I can even erase this. Note that, for example, C infinity functions up to the boundary are certainly contained in the domain of d bar. Okay? And we know that these are probably okay. Let us make it better. C infinity compact support with omega is continued over. Thank you. Okay. Yeah. I'm always thinking of bounded domains, which is not right. Yeah. That's obvious, right? If you take one of those which is in L2 and then differentiate any way you like, it's still in L2 with respect to the power minus phi. So, and these are dense in L2. Even with a weight, there's no problem there. So, therefore, and it is not difficult to check that okay, d bar is closed. This is basically the same as saying that d over dz bar is continuous in the distribution topology. Okay. Okay, I think that is a good place to stop, because after this I'm going to compute the adjoint of this operator, and then I will show that this adjoint satisfies precisely the inequality that is needed by the function analysis lemma. And that will lead to a proof of Hormander's theorem, hopefully sometime tomorrow. So thank you very much.